So today's class will be on the differential calculus of vectors of a vector field. So we introduced the concept of the scalar field and then vector field, and then we discuss the gradient of the scalar field. Then we will discuss the divergence and curl of a vector field. So we will begin. So yesterday we introduced this concept of scalar point functions. A function is defined in terms of space coordinate x, y, z. So that is a scalar point function, and the function value spread over the entire space is called as the scalar field. Similarly, there is vector point function and vector field. So begin with, like yesterday we discussed, a scalar field. Example of a scalar field is the temperature at every point in a room. It's a scalar field. So just look at these examples here. This is wiki here. So a scalar field such as temperature or pressure, where intensity of field is represented by a different hue or color. So throughout, like this is a two-dimensional scalar field, the temperature or pressure, let's say temperature, is continuously varying. Let's say there's a plate and it is being heated at one place and it is in contact with a cooling agent at other place. Red indicates, hot, and blue indicates cold. So there is a variation of the temperature. So temperature is a scalar. So a representation like this is a representation of a scalar field. Now the scalar field can be changing. Yeah. Like this one. There's an example of a scalar field that with time, it keeps changing. So yeah. So there's an example of a scalar field. It's a two-dimensional, but what we discussed yesterday is a three-dimensional scalar field. Now let's understand what is a vector field. A vector field, or it's a vector point function, is let's say velocity vector. Let's say velocity of a fluid particle. Now, a fluid particle velocity is u in the x direction, but it is a function of x, y, z. We will soon understand what is this. V, it's in a matter of space. So velocity of a flowing fluid in space, and w. So this is a vector which is a function. We can say V is a function of x, y, z. but the components of this vector in x, y, z are these. So this is a vector point function. And this is called a vector field. It's very easy to understand. Like, it's a three-dimensional, uh, let's say, a cross section of a rectangular channel through which a fluid is passing. Because I took a rectangular channel for a rectangular room for temperature. Now, for fluid flow, let us consider now the fluid particles. So although they are flowing this way, let's say they come inside, but there may be obstacles that cause the fluid to move like this at every point. And the fluid motion may be very slow at the bottom. So the vectors are slow. It may be faster on the top. So the length of the vectors will change. And then the vectors may change the direction. So this is an example of a vector field for velocity. Velocity vector field. All right. That means at every point in space, every point in space is associated with, it is associated with a vector describing a physical quantity. For example, here it describes velocity. So this is a vector point function. So, so scalar and vector fields. Now, there are many other examples of vector fields as long as in space, um, associated with every point in space or the domain of a three-dimensional domain or a two-dimensional domain, there is a vector associated describing a quantity. That is a vector field, and with time, the vector fields can change, like velocities can change with time. So now to study these fields, we need to understand how the fields change from one point to another. For example, just now we saw this one. So just now we saw this one. Now let's say this is X and this is Y. Now if we move along X direction, how does the temperature change? If I move along Y direction, how does the temperature change? If I move in this, how does it change? So I'm studying the gradient of how the temperature changes uh, in a particular path. So to study this, so we need to understand the del operator. So here we study now differentiation of a vector, more specifically of vector point functions. And the del operator. So consider vector point function. F of r bar. That means r is the position vector. So, or we can write this as f of x comma y comma z. This is a vector. Now, let's say this is a vector function varying with different, so a vector point function f is a vector function varying with different points in domain D. D is a region of volume like that. Now, suppose I want to find derivative of f with respect to t. Then now f, let's say with time, or x, y, and z are varying with a parameter, which usually is time. So I am wanting to see how this function varies with time. Then for that, first, because this function varies with x, y, and z, so this will be partial derivative of f with respect to x multiplied by derivative of x with respect to time. Okay. How does x vary with time? This, yeah, plus partial derivative of f with respect to y multiplied by derivative of y with respect to time, plus partial derivative of f with respect to z multiplied by dz by dt. So now if we look at the differential, so this is with respect to time. Now without reference to any variable, if I just want to find the differential, the change of f, then I get dou f by dou x times dx, dou f by dou y times dy, plus dou f by dou z times dz. Now we can write this as, we observe this can be rewritten as dou f by dou x I cap plus dou f by dou y j cap plus dou f by dou z k cap dot dx I cap plus dy j cap plus dz k cap. Look at this dot product. Dot product of two vectors a1i plus a2i, a2j plus a3k dot with b1i plus b2j plus b3k is a1b1 plus a2b2 plus a3b3. Yesterday we did that. So the dot product of these will give you this. So we have rewritten this in this form. So now this operator, now I'll write I times or I cap times dou by dou x plus j cap times dou by dou y plus k cap times dou by dou z. This operates on f. Okay. And this is nothing but dr, because r is ixi plus yj plus zk. Dr will be dxi plus dyj plus dzk. So this expression is defined as this. We write as del. Okay, del, inverted delta. It is a del operator. We can dot it with r, or del of f, del of f bar dot dr. So we write this. So this operator is called as the del operator, or nabla operator, and is defined as del is I times dou by dou x plus j times dou by dou y plus k times dou by dou z. So this can operate on anything. It can operate on a scalar field, or it can operate on a vector field. So this is the del operator, and this will be very, very useful in various aspects of differentiation of vector fields or scalar fields. Now let us study when del operator is applied to scalar point functions. Del operator to scalar point functions, or del operator applied on scalar fields. That's the idea. So the definition now is that of a gradient of a scalar field. So now the vector function, consider a scalar point function, or first consider a scalar point function f. All right, or in other words, scalar field represented by f. Now the vector function del f is defined as the gradient of the scalar point function or or the gradient of the scalar field. Okay, gradient of the scalar point function f, and is denoted as grad f or del f, which is I times del f or dou f by dou x plus j times dou f by dou y plus k times dou f by dou z. So this is change of a scalar function. For example, temperature. Now, let us take temperature in a three-dimensional space. Or let's take this example. I will take this example. So here there's a temperature that is changing. Let us say temperature is changing with respect to x and y and also z. But here we are taking one particular value of z, that is z equal to 0. And this particular plane is z equal to 0 plane, let us say. And now here the temperature is changing. Now, what does grad f represent? It is representing when I move along x direction and we want to find the gradient of f at some specific point. This will also be a function at some point. Now let us say we choose this point. Now, when I move in this direction, how is my temperature increasing? That is dou f by dou x. Dou f by dou x will give us how is my temperature, how is the temperature here changing at this point and increasing in this direction if I move in x direction. Now, if I move in y direction, so this is dou f by dou x. Now, from this point, if I'm moving in y direction, how does my temperature change? That is dou f by dou y. Okay, and this change is represented by a vector at a point. And now at z direction, that means perpendicular to the plane, how does this vector, how does the gradient change? Now gradient is represented as a vector here because it will give you a direction. The component, if you sum up these three components, you will get a direction of the gradient in a three-dimensional space. But this is the idea, dou f by dou y and dou f by dou x, dou f by dou z. So geometrical representation. Now there are some geometrical interpretations for fields for equipotential surfaces. Geometrical interpretation for del f for equipotential equipotential or isothermal surfaces. These are also called as level surfaces. That means the values of the function is constant throughout this surface. So now let R be xi plus yj plus zk, and f of r bar equal to c, that is f of x comma y comma z equal to c, be a level surface. Now, if it is a level surface, that means it's a constant. It's a constant. Then grad f dot dr. It's a constant, right? So grad f dot dr will be I times dou f by dou x plus j times dou f by dou y plus k times dou f by dou z dot of I dx plus j dy plus k dz. So this dot product is nothing but dou f by dou x times dx plus dou f by dou y times dy plus dou f by dou z times dz, which is df, which is differential of f. And because it's a level surface, the differential is zero. Across the surface, wherever direction you move, you get zero. So we get, what is dr? Dr is a tangent. Yesterday, we discussed this. Dr, what is dr? Is, r of, say, t plus dt minus r of t. This is a tangent at a point t. So, or this is now, if it is in terms of x, y, z, this is, so tangent at a point x, y, z on the curve, on this level surface. Now, since del f dot dr is 0, which implies del f is perpendicular to dr bar. So therefore, dr bar is tangent to the surface. So del f represents a normal to the surface f of x comma y comma z is equal to c. So for a level surface, gradient is this. Okay, level surface are points of equipotential lines. In fluids, we have, equipotential lines, and in we also have the concept of equipotential lines in electrostatics. So wherever the function value is constant along a path or a surface, so on that surface, grad f represents the normal to the surface. Other than that, grad actually represents the variation of a physical quantity, which is a scalar. So grad f represents a variation of physical quantity in terms of x, y, and z directions, a combination of that. Next, very, very important concept, extremely important concept in this category of Del operator applied to scalar point functions. First is definition of scalar field and definition of gradient of a scalar. This is definition of gradient of a scalar field. So next is the definition of directional derivative. Now I want to find, see just now I checked, if I go in X direction, how does the temperature change? If I go in Y direction, how does the temperature change? Now I want to know if I go in a particular direction here, how does my temperature values change? Or whatever is the scalar point function, how does it change? So that is the concept of the directional derivative. So the rate of change of the scalar point function f in the direction of vector A of a vector A bar is called as the directional derivative. It is called as the directional derivative of f along A bar. Directional derivative of f along A bar, and is defined as gradient of f dot A cap. So this is the directional derivative. So gradient of f dot A cap is the component of del f along or in the direction of A cap. Yesterday we discussed how dot product is dot of A dot B. We talked in terms of the projection. Projection of A over B is the dot product. So del f dot A cap. So projection of a vector A along a vector B was A bar dot B cap. That was the projection. So same here, grad f dot A cap is the projection of the gradient del f along A. So del f dot A cap is the directional derivative. So now when will this directional derivative be maximum? When both grad f and A cap are in the same direction. That means if we take the component of the directional derivative along the component along the gradient, then it will be the maximum. That is a common sense thing. Next, properties. Properties of this gradient. Properties of gradient. So the first one, gradient of f plus g, two components, is grad f plus grad g. Now gradient of f times g is f times grad g plus grad f times g. It's not a dot, it is, these are scalars. Next, gradient of f upon g is denominator g square, g times grad f minus grad f times g. Okay, so these are some simple properties where f and g are scalar point functions or scalar fields. All right, now a definition of conservative vector field. This concept comes in fluid mechanics and also in um, electromagnetics. So a vector field f bar, which can be derived from a scalar field f such that f bar is grad f. So small f is the scalar field and gradient of the scalar field is this vector field f. Then such a field f is called as the conservative vector field as a conservative vector field. And f is called as the scalar potential. Scalar potential of the conservative vector field f. So a vector field f bar is called as a conservative vector field if it can be derived as gradient of a scalar vector field, and that scalar vector field f is called as the scalar potential of f bar. So this is about gradient. Let's see if one or two examples of this gradient. I'll just see. Okay, let's take this example. Let a function f be defined as x square y cube z power 4. Okay, then find the gradient of f at some point, say 1 comma -1 comma 1 comma -1 comma 1, let's say. Now let us find this. So solution, how do you find the gradient? Now grad f is defined as dou f by dou x I cap plus dou f by dou y j cap plus dou f by dou z k cap. So dou f by dou x, it is 2x y cube z power 4 I cap. Now plus 3x square y square z power 4 j cap plus 4x square y cube z cube k cap. So what did I do? Partial derivative of f with respect to x. So keeping others constant, derivative of x square is 2x. Then partial derivative of f with respect to y. So keeping the other two constant, differentiating y cube, we get 3y square. Then next, keeping x and y constant, differentiating z power 4 with respect to z, we get 4z cube. Now, the gradient of f at this point, 1 comma -1 comma 1. So substituting, we get 1 -1 1. So we get a negative value -2i. Here we get all positive values plus 3j. And here we get again a negative value, y cube negative value. So we get -4k. This is the gradient. So partially, if we go along x, we get -2. Partially, we go to differentiate along y, we get this, and differentiate along z, we get this. Let me just show you an animation of this. Let me see if I can do that. Not this one. Yeah, this one. Now this is a good animation to see. So this is a function here z. This function in terms of x and y. Now what x value is fixed and we are moving along y, and then the function value is changing. So the function value is changing as we move along the direction of y. So what we are calculating is dou f by dou f by dou y. X is constant, treating x as constant. So along this line, now the slope of this particular line, this line is the gradient. This is the tangent. At any point, what we are getting is the tangent. So you have got the negative value and now the 0. Again, I'll show it is 0, slope is 0. Then slope goes negative. Then the slope goes positive. Comes to 0 slope. Again, the slope is increasing. Then the slope becomes 0 and then again decreasing. So this is, of course, partial derivatives. We have now at any given point, this direction of this line is a vector. Now, as x changes, let us say we go to another point x and change, and again we get this. So dou f by dou y, dou f by dou y, we get a tangent like that. It's a slope. Slope of this line gives us dou f by dou y. It is the value. Now, how does the slope change along x? So, all right. So this is along x. The same thing along x. Now, along x and along y, when we show a vector, so you get a gradient in this form. So you just understand the arrow, direction of arrow is showing the value of the gradient. And as we move from one point to another in the field, how the gradient changes is shown in this video here. So this is now we did it with respect to x, y, and z. So there's a vector in a space. To show the graph like that, that was a z function was defined in terms of x and y. So it was easy to show that way. But this is a three-dimensional, the domain itself is three-dimensional, and f, let's say, is a temperature, or f is a pressure at that point. So how does it change in a particular direction? So another question, example 2 of gradients. Find the unit normal. Find the unit normal to the surface xy plus yz plus zx equal to 3 at the point 1, 1, 1, 1, 1, 1. Find the unit normal to the surface, this one. So this is of the form f of x, y, z is equal to constant. So this is a surface. This is a surface, and we call it as the level surface. So grad f normal at a point to the surface is grad f. So grad f, or you say n bar, is grad f dou f by dou x I cap, dou f by dou y j cap, plus dou f by dou z k cap. So differentiating this partially with respect to x first, we get y plus z. Then differentiating f with respect to y, we get x plus z. And differentiating f with respect to z, we'll get y plus x. Now at 1, 1, 1, n bar or grad f is equal to, substitute 1, 1, 1, you get 2i plus 2j plus 2k. 2i plus 2j plus 2k. All right. Now unit normal in that direction. So n cap is n bar by modulus of n bar. So 2i plus 2j plus 2k under root of 2 square plus 2 square plus 2 square. So 2 comes out, you get I plus j plus k upon root 3. So 1 by root 3 I plus 1 by root 3 j plus 1 by root 3 k. This is the unit normal. All right. So this is an example of an equipotential surface. And how do we find the unit normal to the equipotential surface? So first question was simply about gradient, finding the gradient. Second was about finding the normal to the equipotential surface, some equipotential surface. Now let's find the directional derivative. For the first question itself, we'll do for the same question as one, find the directional derivative of f at, what was that point? Yeah, at 1 comma minus 1 comma 1 in the direction towards the point 2 comma 3 comma 4. Let us see. So solution. Now grad f, we found grad f is this. Now we found this out. Grad f at 1 comma minus 1 comma 1 is equal to minus 2i plus 3j minus 4k. This we found out in the first question. Now a bar. So from this point to this point, what is the vector? So a b bar is b bar minus a bar. B bar minus a bar. So 2 minus 1 is 1 times I. 3 minus of minus 1 is 4 times j plus 4 minus 1 is 3. Okay. Now what is a cap? I plus 4j plus 3k divided by under root of 1 square plus 4 square plus 3 square. So under root 26. So 1 upon under root 26 I plus 4j plus 3k. Therefore, the directional derivative of f along a bar is del f dot a cap. So we have minus 2i plus 3j minus 4k dot 1 upon root 26 I plus 4j plus 3k. This we get as 2 into minus 1 minus 2 into 1, that is minus 2, plus 3 into 4, 12, and minus 4 into 3, minus 12, divided by under root 26. So we get minus 2 upon root 26. So this is the value of the directional derivative. Now the directional derivative will be a scalar quantity. So there's one example. There are many other examples we can take, but this is the concept of the directional derivative. Okay, I'll move forward and we'll do more problems from gate. But before that, I'll move forward to other concepts. I have to discuss curl. I'm sorry, I have to discuss divergence and curl. So del operator applied on vector point functions. Del operator applied on vector point functions. So on a vector, either you can do dot or you can do cross. So very important divergence of a vector field. So divergence of a vector field or divergence of a vector point function. Now this is defined as del dot f, or you can write this as divergence of f. This is, see what it is. It is I dou by dou x plus j dou by dou y plus k dou by dou z dot f. Whatever f is, it has, let's say f is x component. It is a function of x, y, z. Each one is a function of x, y, z. This is the y component and this is the z component. So this is I plus fyj plus fzk. Now, when we do a dot product, this operator operates on f, and I dot I is 1, I dot j is 0, I dot k is 0, j dot I is 0, j dot j is 1, j dot k is 0. So we only get I dots with I, j dots with j, k dots with k components. So we get this as dou f x by dou x plus dou f y by dou y plus dou Fz by dou z. This is the divergence of a vector field. Del dot F is called as the divergence of a vector field. Now, this is a scalar. Important points to note. The value is a scalar. Del dot F is a scalar value. So it is a scalar field. Okay. Now note, very important, del dot F is not equal to F dot del, because F dot del, you will get F dou by dou x of something. It has not yet been operated on something. The del operator has not been operated. It is preceded by F. So these two are not equal. This we should consider. Now look at its physical representations. This has a lot of connotation in fluids and also in electromagnetism. Let's see. Now, there is a beautiful video, very beautiful video, which you can watch this. 3 blue, 1 brown video on this. So I'll just try. Yeah. Just a second. I'll just share this video with the sound.
And artificially shorten ones that are too long, maybe using color to give some vague sense of length.
I hope you are able to hear.
Now in principle, on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the...
So yeah, we are representing a vector field of, a flow of a fluid, let's say. So at flow of a fluid in space, at different points, you have different velocities. And with time, that velocities are also changing. And sometimes it may not change, it may be of constant velocity. But at any given point of time, you get a vector field like this.
Force of gravity at many different points in space.
This is another
or maybe a
vector field of, gravitational pull.
Magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And
what he's saying is usually the vector fields, although it may be talking about electricity or magnetism, but we can describe the vector fields in terms of another physical quantity. For example, fluid flow, and that will give us a better appreciation of this concept of vector fields and the divergence and the curl. So let us go through
What
that.
can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness.
So there's a concept in fluid, like let's say there's a hole on a plate, and below that there is a water body, and then the fluid starts to come into out of that hole and onto the plate. So the fluid comes out from the bottom, and if we are studying this area, it is like a source, fluid source. So for a source, the vector fields, the direction of vectors move away from the source. It's so these are sources, okay, of a fluid flow. So there's a vector field.
As if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness.
Now, let us say the fluid flows and then there is a hole and the fluid disappears. Then this is a sink. For example, our wash basin sinks. This is a little different type of a sink than the wash basin sink. Here, fluid comes and just disappears at this point. All right. Wash basin sink has a rotational effect around it, but so this is a sink. So source and a sink are very useful.
The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near.
Divergence says, now at a given point, divergence means it is measuring that. I'll just go back and forth from this video. It will help you. Now, divergence at a point. You take a small region, this may be a three-dimensional region. It need not be a two-dimensional region. It can be a 3D region around that point. A small, this is that point, a 3D region around it. So now, divergence means if the difference between the inflow vectors and the outflow vectors, if the outflow is larger than the inflow, if the outflow is larger than the inflow, then the divergence will be positive. Okay. If the inflow, so let us consider this as water flowing here. If somehow this inflow is lesser than the outflow, then that means in this region, it is acting like a source, like a fluid source. That fluid is getting added. So this is like a source. So you get a divergence as greater than 0. But suppose you have that inflow is greater, but the outflow is less, then that means the divergence is negative. And suppose you have a constant fluid velocity field, that means if you choose a region, the flow of water into this region and out of this region is the same, then the divergence will be 0. This is the case in fluids. Those of you who have studied fluid mechanics, this is a case of incompressible fluid flows or incompressible fluid flow. The divergence of the velocity vector field will be 0. So let's go back now. Now you'll understand this video, what he's saying.
All right. For example, the divergence of our vector field evaluated at all of those points that act like sources will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate.
So that's the connotation of divergence. So divergence represents many things. So if V is, say, Ui plus Vj plus Wk represents fluid velocity at a point P, then del dot V bar gives the rate at which the fluid is originating. At the point per unit volume. Of course, per unit volume, we are talking about the rate. So at any given point, whether it is like a source or sink, at that region inward, whether the incoming velocity or the vector field is greater than the outgoing, it will be a sink. If it's the outgoing is greater than the incoming, it will be this. So note that for incompressible fluid flows, incompressible means the fluid cannot be compressed. So for incompressible fluids, so del dot V will be 0. Okay. And this is the continuity equation, what we call the differential equation of continuity for incompressible flow is this in fluid mechanics. Now in electric field, this is an electric flux. If V represents electric flux, then del dot V represents the amount of flux that diverges from that point. So when you say del dot V is negative, then it converges at that point. Okay, now this can also be representing for heat flux, and very important for this electric flux, del dot V equal to 0 everywhere. Is 0 throughout the field. Then such a function is called solenoidal vector function. This is called as the solenoidal vector function. All right. This is particularly representing the electric flux. Now, next to properties. This was the physical interpretation, and next the properties of this divergence. Now, divergence or del dot of two functions a bar plus b bar is del dot a bar plus del dot b bar. Then del dot a scalar quantity times, or to avoid confusion, we'll write this as k times a bar is k times of del dot a. Oh, okay. If it's a k is a constant. Now, if it is a potential, it is a scalar field multiplied by a. So first you get del f dot a plus f times del dot a, where f is a scalar field. A is a vector field, f is a scalar field. So if this is a product, then it is del f dot a, okay, plus f times del dot a. So operator first operates on first one, treating the other as constant. Then it operates on the second one, treating the first as constant. So when it operates on the first, del operating on scalar point function gives you gradient. So grad f dot a, and del operating on the vector point function has to be del dot a. So this is how it is defined. Next very important topic is, the curl of a vector point function, or curl of a vector field. First one was divergence. Next is curl. Curl of a vector field. Now, curl is defined as curl of F is defined as del cross F. Now, if F is a function having X component, Y component, and Z components. Okay, these are not functions of X, Y, and Z. Each one can be a function of X, Y, and Z, each one. But this is just a component in I direction, component in J direction, and component in K direction. So now, then, how is del cross F defined? So we know it's an operator. So it will be like this: I times dou by dou X plus J times dou by dou Y plus K times dou by dou Z crossed on now. How do we do cross product of two vectors? It is determinant of I, J, K. The first elements of the first one and the elements of the second one. So now we get this, you see this, I times dou Fz upon dou Fz by dou Y minus dou Fy by dou Z. Now minus of, or I will write plus of. If it's minus, then this way minus this way. Now it will be this one minus this one. So this one is dou Fx by dou Z minus dou Fz by dou X plus K times dou Fy by dou X minus dou Fx by dou Y. This will be the divergence, the curl of a vector field. Now, curl of a vector field is also a vector. Curl of a vector field is also a vector, that is to be understood. And now let us understand the interpretation. What does this mean? See, curl, now consider a velocity field. Now we will just restrict ourselves to fluid velocity in a two-dimensional system. Okay. Maybe we'll yeah. This is X, this is Y. Now let us say let us simply take, what does this mean? We will consider flow in the z direction to be 0. Let f represent be a velocity vector field for fluids. It has ui plus vj plus wk. U is the velocity component in the x direction. Now let us say take a vector field like this. That means that fluid is flowing at any given point. The velocities along the x direction, it is not increasing as we move along x. But let's say the velocities are increasing in the y direction. At any given point, velocity is increasing. And here the velocity is smaller as closer to the x-axis. And on the x-axis, velocity is 0. Right? Now what happens? This is, so now if I am moving along x direction, and here these are all components u. These are, what are these components? These are u only. These are u components because it's a direction of velocity in x direction. The magnitude of velocity in x direction is u. Now along x direction, dou u by dou x is 0. No problem. Now, but dou u by dou y, dou u by dou y, that means when I'm moving in the y direction, what happens? My velocity components of u, when I'm moving along y direction, it is increasing. So when it's increasing, so I get dou u by dou y as constant. So f of x is u, f of y is v. You can omit this. So I have this, let's say this is 0. For this particular vector field that I have drawn here, this particular vector field is simply u times I. All right. So all the components will be 0. Fx is u, Fy is 0, Fz is 0. So now what we get, curl, we'll get two components. Now with respect to z also, we are not considering. So this term is also gone. So we are left only with this term. So curl for this, if you look at the curl, del cross v is I dou by dou x plus j dou by dou y plus k dou by dou z. When I cross it over I, now I cross I is 0, and of course I am considering only in plane, so I am not considering fluid flow in 3-dimensional. So this term I omit. So I just have this. I cross I will give me 0, but j cross I will give me minus k. So I get dou u by dou y with k cap with a minus sign. And you substitute in this, you get that only. Minus dou u by dou y, k cap. All other factors are 0. Okay. Now, this curl, what does it represent? It is giving me some value and it is giving a direction. It is giving a direction. What direction? It is giving a direction into the plane of xy. It is an arrow as if you're, penetrating this plane, xy plane. What it is saying is, now if we put one stick, let's say matchstick. If I put a matchstick, as the fluid is flowing, I put a matchstick like this. Now what happens? Because the flow in the top is greater than the flow in the bottom, this matchstick will tend to rotate. So curl gives that amount of rotational effect of the vector field at that point. That means if I put a matchstick there, how does it rotate? That gives me the idea of curl. So when you see this particular vector field, it looks like a straight line. It appears that there is no curl. We may consider curl means vector is curling around, the vector field is curling around like this. No. Curl means if I place one object in the vector field, does it have a rotational effect on that vector field, on that particular object? That is the idea of curl. Okay, this example must help you to understand this basic concept. Now the same curl can be experienced. Now you can have further. We can have many changes now. U need not be constant along X. Right now, if we move in this direction, U is constant. U can keep increasing with X. Then your curl values will change again. Also, velocity may be having components. Instead of having just the X component, velocity may have different components, Y and Y component, purely Y component, or mixed X and Y components. Let's say flow is in Y direction only. And again, we have the same thing that the flow is more on one side. As we are moving across X, the flow is increasing. Or they can be at any given point, the field has two components, both X and Y. And the resultant is this. Now, in each of this, what is a curl? So you put an object, right? Maybe with an arrow to understand. Now, how much rotational effect does the vector field offer in that direction? That means if you move along X and move along Y, the gradient forms a vector and the gradient rotates. So it is an indication that if I move in this region, there is a rotational effect. So these are very, very key concepts for vector fields. So generally, I'll just give some beautiful illustrations, very beautiful illustrations. You just watch. So physical interpretation of curl is this, a rotational effect that it has. So a vector field whose curl is 0 is called as an irrotational vector field. It is called as an irrotational vector field. that means you don't have a rotational effect at all. And if vector curl is not zero, then it is a rotational vector field. They're very beautiful fluid mechanics experiments in this, which people can demonstrate for curl and this. Now, if in a rigid body rotation, about a fixed axis O, the axis is passing through, axis has to be a straight line, axis passes through origin. So if omega is omega xi plus omega yj plus omega zk is the angular velocity, then the tangential velocity v of any particle at PR of the body or on the body is given by V is equal to omega cross R. V is omega cross R, which we know we have done it. This is in physics. V is equal to R omega. We have done that. But in terms of, see, we have done in a plane. In XY plane, there's a circular disk. We have done problems of this type. Now there's a circular disk, and then the XY plane, and it is rotating like this. But now this kind of a vector, so angular velocity, if this is the XY plane, the angular velocity will only have the Z component here. Okay, it doesn't have the X and Y component. That means rotation is about the Z axis, right? These are the types of problem we must have done in physics, but they are three-dimensional objects. Let us say football is hit on a football ground and it is rotating, and at the base of the football ground you place X and Y, and Z is the elevation. Now the football is not rotating just along X axis or along Y axis. It is moving, rotating maybe along a completely inclined axis. All right. It has a rotational component in X direction, rotational component in Y direction, and rotational component in Z direction. Isn't it? It rotates in not just in, okay, it not just rotates in X, it rotates in Y, it rotates in Z, it rotates in Y. So that is this represents, and then V dot. So that is the usefulness of vectors. Usefulness of vectors is if you are able to write vector forms of physical quantities, you need not comprehend from physical view of all angles. You just do the vector products, you will get your final answer perfectly right. That is the great advantage of vector calculus and vector algebra. So now some very important result. I don't know how much you understood this part, this football example. You think about it. Football is not just rotating when the kick is given, the ball is flying like a projectile, but at the same time, there is a rotation. It may rotate along X, along Y, or along Z, but actually it rotates along some axis. That axis of rotation is this. This gives the direction of that axis. Now, curl of this vector, curl of this velocity vector is shown to be twice of the angular velocity vector. This is an important result in mechanics. Curl of a tangential velocity vector field is twice the angular velocity vector. Okay, now for the same problem here in 2D, we know that the tangential velocity at the center is 0. Now let's say it is rotating like this. So the velocity, tangential velocity vector here will have some value r into omega z. Here it will be greater. Here it will be even more greater. And here it will be even more greater. This is the velocity. This is angular rotation. The tangential velocities at this point will keep increasing like this. So, and then throughout it is like this. Then along any other inclined line, the tangential velocity vectors will be like this. So this is the vector field. We are just drawing along 3 lines, but at every point on this circular disk, at every point you can draw a tangential velocity vector. Now, the curl of this velocity vector. Now, this velocity vector is keeping on changing. It is omega cross r. Omega cross r, and it keeps changing. And del cross omega cross r is how is this velocity vectors changing in x, y, and z direction. So of course, when only we are considering a k component of omega, r will be having x and y component. So z component omitting the z component, we can show that this is equal to 2 omega. You can try this out, this simple problem. You can try this out. Now I will go on to show the curl.
An arbitrary vector field around the point.
Yeah.
Fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom but quick up top, resulting in a net clockwise influence. And really, true proper curl is a 3-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content from my time at Khan Academy describing this in more detail if you want, but for our main purpose, I'll just be referring to the 2-dimensional variant of curl, which associates each point in 2D space with a single number rather than a new vector. As I said, even though these intuitions are given in the context of fluid flow, both of these ideas are significant for other sorts of vector fields. One very important example.
So this was curl. Now in Wikipedia, you can type geogebra.org for divergence and curl. You will come across this page, very interesting page. It says this applet allows you to visualize vector fields and their divergence curl, as well as work done by the field. We are not, that is integral. So along a path, I am changing the path. I'm not doing the path at the moment now. Okay. I'm ignoring this. Now the field can be this. What is this? This is f of the function I comma j. This is a vector field. It's two-dimensional. We are not going three-dimensional. So this is x square plus y square I cap, x square plus y square j cap. Now there is x I cap plus y j cap. This is the vector field, x I cap plus y j cap. So you see, this is the divergence. This is divergence and this is curl. Now, at any given point, the divergence is fixed. And at any given point, the curl is 0. Look at this now, examples. So let's say f xi plus yj. This is the vector field. Now del dot f, divergence. So you get dou fx component by dou x plus dou fy component by dou y. When you do dot product, so you get dou x by x, that is 1. Dou y, fy is, y component is y with respect to y is 1. So divergence is 2. That's what throughout, irrespective of I comma j, the divergence is 2 throughout this field. Look at the curl. I, j, k, dou by dou x, dou by dou y, dou by dou z, x, y, 0. We get I times 0 minus derivative of y with respect to z is 0 minus j times derivative with respect to x of 0 is 0 and derivative of x with respect to z is 0 plus k times derivative of y with respect to x is 0 because there is no x component. Derivative of x with respect to y is also 0. So we get a 0 curl. So for this particular field, you see divergence is 2, curl is 0. And see the vector field, how it looks. This is the center origin. Now from the origin, further you go, let's say 3.3, 3,3 is the point you go to. 3,3. The vector is 3i plus 3j, xi plus yj. So at any given point, this is like that. So any given point, the divergence is 2. You can see it looks like a sink that is opening up. And at any given point, the vector, inflow vector is lesser than the outflow vector. Therefore, the divergence is 2. Now look at some other vector field. Divergence is 0. Yeah, this is on. This is a vector field which is minus yi plus xj. Now the curl is constant. No matter where you go, curl is 2. And no matter where you go, the divergence is 0. That means inflow and outflow at any point is 0, whereas there is a rotational effect here. Okay. And we can calculate. Let us do a calculation for this. This is a very simple vector field minus yi. So F is minus y times I cap plus x j cap. So del dot F is so k component itself is not there, I dot I. So derivative of y with respect to x partial derivative 0, 0 times I, not I. It is dot product, so it is a scalar. So you get minus dy by dx plus dx by dy, both are zeros. Both are independent functions. Curl dou by dou x, dou by dou y, dou by dou z, minus y, x, 0. So I times 0 minus 0 plus or minus j times 0 minus 0 plus k times, interesting, dou x by dou x 1 minus of minus dou y by dou y minus 1. So minus of minus 1. So you get 2k. So the curl is 2k. That is what we see. At any given point, it is constant. Now this vector field x square plus y square and x square plus y square. Now the divergence is changing. Divergence is 0 at the origin. At all other places, the divergence is negative. In this region, the divergence is positive of the field. Curl, negative. At some points, it will be 0. Maybe along a particular line, it may be 0, is what I feel. Along y equal to x, I think it's 0. Yeah. And then it is negative, very increasing. You can see the speed 0, positive, increase speed, positive. You can try this. So this is the idea of the divergence and curls of vector fields. I hope this class gave you an interesting picture of what divergence and curl is. Generally, we just in colleges I've seen, they just teach it as just some mathematical, abstract mathematical operation, but it has very deep physical significance. which if you understand, then you will relish, especially a course like electromagnetics and course on fluid mechanics. When the kinematics of the fluid particles, if you know the vector fields well and the concept of divergence and curl, you will understand what we are talking about. Now, properties: curl of sum of two vectors a plus b is sum of the curls of the individual ones. Now, curl of a constant, right, so vector, constant times the curl of a vector. Now, if we have a scalar field as we did last time, now we get del f cross a bar plus f times del cross a bar. Very important, conservative vector field. Conservative vector field. Now, v bar. For that, curl of v bar, that is del cross b, will be 0 for a conservative vector field. Previously, we said for a conservative vector field, we can write the vector field in terms of the gradient. Here, f is equal to grad f. So for a conservative vector field, it's a very important thing. The curl of any conservative vector field is 0, because I can write this as del cross of del f, and we can show that this is del cross of del, which is 0 times f. You can show this is 0. Conservative vector field we can always write in terms of the potential. Okay, so I hope you like this class. This is one of the most important classes, and in fact, earlier when I used to teach fluid mechanics, I would first teach vector calculus before I began fluid mechanics, because students will have a better comprehension of fluid kinematics. Otherwise, they don't understand what it is all about. All right, so I stop this class today. I will be sharing a assignment in Moodle. Of course, it has integrals also, but what we need is till whatever I have taught today, you can do it. You can solve up to curl. You can start practicing. Some of the problems we'll do in the class in the next session. All right, thank you. I'll close. Next session will be the higher order del operation. That means second derivative. Now, del is the first derivative in the vector form. What about the second derivative? So we deal with the concept of Laplacian operator. It's another important concept in vector calculus that we do in the next class. Thank you.